Welcome back. So far we have learned to take derivatives of a few particular functions, namely any polynomial, plus sine and cosine. We have also learned some structural theorems, namely the two linearity properties that allow us to take derivatives of sums and constant multiples of those functions. We have two more structural theorems on the menu today, the product rule and the quotient rule. And these will tell us how to take derivatives of products and quotients of functions. We have seen already that the derivative of a sum is the sum of the derivatives. But as I warned you in the last lecture, the derivative of a product is not the product of the derivatives. And an easy example will make this clear. The derivative of this product, x squared times x cubed, is something that we can easily compute because we can simplify the function itself, rewriting it as the derivative of x to the fifth. And we know that is 5x to the fourth. On the other hand, if we took those two derivatives separately and then multiplied the results, we would end up with 2x times 3x squared, which is 6x cubed. Very different from what we obtained over here. That means that these two expressions are unequal. So if you are looking for the derivative of a product, do not be tempted to compute the product of the derivatives. If you do so, you will be led astray. Okay, but what is the derivative of a product? What is this mysterious product rule that will allow us to take the derivative of a product? It's actually pretty easy to come up with the product rule. There are a few ways to do it, the most straightforward and mechanical of which I've given in the book, but I figured in this video I would show you another way to do it, which is a little more geometrical. Let me move this out of the way. That's better, and I will put a question mark here for now. For this derivation, I'm going to represent the values of these two functions, f and g, by the sides of a rectangle. The idea is that for any input x, we'll get these two outputs, f of x and g of x, and we will represent those as the lengths of these two perpendicular line segments. So if some input x makes f of x very large, then this line segment would be very large. And if it makes g of x very small, then this line segment would be very small. For any input, we get these two lengths. And I will go ahead and complete the rectangle of which they are part. Its area is f of x, g of x, which is precisely the function whose derivative we want. Good, so we've represented this function as an area. Now, we're looking for the function's derivative. That means we're looking to find how the value of this function, this area, changes in response to changes in the input, namely to infinitesimal changes in the input. Well, if we were to change the input of the function from x to something infinitesimally more than x plus dx, these two lengths, the sides of the rectangle, would also change by an infinitesimal amount. Now, they might get infinitesimally longer or infinitesimally shorter. For the purposes of this demonstration, I'm just going to assume that they get longer because it will make the argument easier to follow. You have to make a few adjustments if they get shorter. Anyway, if that's the case, then after the little infinitesimal nudge to the input, we might end up with a rectangle like this. Our original rectangle with this little L shape tacked onto it. And remember, these are infinitesimal changes. This is the infinitesimal change in f of x, so I'll label it as such. And this is the infinitesimal change of g of x. And I issue my standard warning. Obviously, we can't draw infinitesimals. These are gross exaggerations, but it's just a schematic figure, so they will do. Now, this length is the infinitesimal change in f, and this length is the infinitesimal change in g. But what about this area, the area of the L shape? That infinitesimal increase to the area is the infinitesimal increase of f of x, g of x, because that's what is representing area here. So let me label that accordingly. Well, this is a good thing to see, because if we're looking for the derivative of f of x, g of x, we know that's a ratio of infinitesimal changes. The change in output over the change in input. And you might say, okay, well, we've got d of f of x, g of x, but where's plain old dx? I don't see it anywhere in this picture. We actually won't need it. What we'll do is we'll come up with an expression for this thing, and then we'll just divide by dx. Watch. This expression is the area of this L shape. And it's easy to come up with the area of an L shape. You just break it into three rectangles, like so. And now we'll just find the area of each one, and we will add them up. And that will give us our expression for d of f of x, g of x. Well, the area of this first one is, of course, the product of its two lengths, one of which is d of f of x, and this one is not labeled here, but of course it's the same thing as this side, which is g of x. So the area of this first rectangle is going to be d of f of x times g of x. Now let's get this other one up here because it's so similar to that. This one is going to be the length of this side, which is of course f of x, times the length of this side, which is d of g of x. So we'll have to add in f of x times d of g of x. And all that remains is this little piece in the corner. What are its dimensions? Well, this length is d of f of x, and this length is d of g of x. So their product is d of f of x times d of g of x. Aha! That is a product of infinitesimals. It's an infinitesimal bit of an infinitesimal bit, and therefore we may treat the area there as 0, which I will then immediately erase just to clear out the clutter. Excellent! Now we have d of f of x, g of x. To come up with the derivative we want, the derivative of a product, all I have to do is divide this thing by dx. And when I do that, I end up with all of this stuff over dx. And we can simplify this expression just by rewriting it a little bit. We'll break it into a sum of two fractions, like so, and then we'll split each fraction into a product, like this. And now we are staring at the product rule, because this factor right here is just the derivative of f with respect to x, and this factor right here is just the derivative of g with respect to x. So, if I were to rewrite this in terms of prime notation, I would get f prime of x, g of x, plus f of x, g prime of x. And this easy-to-remember expression right here is the product rule. To take the derivative of a product, you end up with two terms, the derivative of the first times the second, plus the derivative of the second times the first. To confirm that this works, let's go back to our example from before. We were considering the derivative of the product of x squared and x cubed. Of course, if you were actually faced with computing this derivative, you wouldn't use the product rule. You would just say, well, that's x to the fifth, and therefore its derivative is 5x to the fourth. But just to confirm that this gives us the correct answer, 5x to the fourth, let's use it here. To apply the product rule, we'll take the derivative of the first function and multiply it by the second function itself, which gives us 2x times x cubed, and then we have to add on the next term, which is going to be the first function all by itself times the derivative of the second function, and therefore x squared times 3x squared. But of course this first term simplifies to 2x to the fourth, while the second term simplifies to 3x to the fourth, and when we add these together we get 5x to the fourth, which is exactly what we know the derivative really is. Good! But as I said, you wouldn't actually use the product rule to compute the derivative of something like that. A place where you would use it would be something like this, the derivative of x cubed times cosine x. Well, according to the product rule, the derivative here will have two terms, the first of which is the derivative of the first times the second function, therefore 3x squared times cosine x, plus the second term, which is the first function just sitting there times the derivative of the second, x cubed times minus sine x. And of course, no one in polite society would write it like that. We would put this negative over here and write this. And that's it. One more example. In the last video, we ended by looking at the derivative of the product sine x times cosine x. And we found this by rewriting this with a double angle identity as half of sine 2 of x, and then we did that chain rule trick to come up with the derivative. But we did not have the product rule at our disposal then. If we wanted to compute this with the product rule, we would get the derivative of sine x, the first function, times cosine x, the second function, plus sine x, the first function, times the derivative of cosine x, the second function. And we know the derivative of sine is cosine, and the derivative of cosine is minus sine, so we can rewrite this line as cosine times cosine plus sine times minus sine, and we'll wrap this up in a nicer package as cosine squared x, because that's what that notation means, minus sine squared x. And now some of you might think back to the end of the last video and say, wait a second, there we found that the derivative of sine x cosine x was cosine of 2x. What is this stuff? Well, to repeat my warning from last time, you must know your double angle identities for sine and cosine. And if you do, you recognize at once that that thing actually is cosine of 2 of x. So we have reconfirmed what we found last time by a different method. Okay, that is the product rule. Very easy to remember and very easy to use. Now we will turn our attention to the quotient rule, which is a little harder to remember, but just as easy to use. We will be looking for the derivative of a quotient. What will that be? We shall soon find out. As I mentioned earlier, the derivation of the product rule that I just gave you in this video differs from the one in the book, and I'll do the same thing with the quotient rule. I'll give you a slightly different derivation here for the sake of variety. So let's let y be this quotient f of x over g of x. We want to derive a recipe for y prime, the derivative of this thing. So here's our derivation. Since y is defined as f over g, we can rewrite this thing, if we clear the fractions, as f of x is g of x times y. Now why would we do this? Well, this gets rid of our quotient and turns things into a product. G is a function of x, and of course y itself, this quotient, is a function of x. So maybe by applying the product rule here, I can end up with an equation that will involve y prime, and then I will just be able to solve for y prime, which is, after all, what I'm looking for. So let's try that. F prime of x is going to be g prime of x times y plus g of x times y prime, just by the product rule. Well, this is good because now we have y prime, the thing we're looking for, in our equation. So let's just solve for it. When we do, we get that y prime is this expression right here. At this point in your mathematical career, you should be able to write that down in one shot, but if you can't, just make sure you confirm it on your own. And we're nearly done. The only problem with this expression on the right is that I still have this y here, but I can always replace y by its definition in terms of f and g. So when I do that, I get this, and now everything is in terms of f and g, which is good, but we can clean this up and just write it in a prettier form, because there is nothing so ugly as fractions within fractions. So let's start by putting everything in the numerator here over a common denominator of g of x, like this. And so now we have this fraction, which is divided by g of x, and of course dividing by something is the same as multiplying by 1 over that thing. And if I were to multiply this by 1 over gx, I end up with this thing, which is still unpleasant, but at least we no longer have fractions within fractions. And we are pretty much at the end of the road. All I'm going to do at this point is reverse the orders in those multiplications just to put this in a slightly more memorable form. I'll do that and I'll bring it up here. And here it is. That ugly expression is our quotient rule. And as I said before, it's a little harder to remember, but it's not that hard. Everybody remembers that in the denominator you get the square of the bottom function. That's easy. It's the top that people sometimes screw up. And even it looks kind of like the product rule, so it's not hard, except that we have this negative, which means that you have to be very careful of which one comes first. Otherwise, you'll get the negative of the thing you were looking for. Fortunately, there is a silly mnemonic device that will fix it in your memory. I did not know this silly mnemonic device until the first time I was actually teaching a calculus class. And I remember grading an exam in which a student had written on the top something like, "Heidi-ho, heidi-ho," and I remember asking him afterwards, "What is this?" And he told me it was something that he had learned the first time he took calculus. And the actual little jingle goes like this: low-d-high minus high-d-low over the square of what's below. And the way you interpret this little thing is that the quotient rule involves the derivative of a quotient. So you've got a high function and a low function. And what is the result of taking the derivative of that quotient? Well, low d high, that's this thing right here. The low function times the derivative of the high function. That's what d high means. Don't think of that as d like our little d infinitesimal change. That's standing for derivative. Derivative of the high. So low d high minus, and what's this? High d low. The high function times the derivative of the function at the bottom over the square of what's below. And if you remember this dopey little thing, you will never forget the quotient rule. So let's put it to use in a few examples. In the previous lecture, we found the derivatives of sine and cosine, but we still haven't found the derivative of tangent. You might wonder if this is going to require another elaborate geometric proof, like those we used for sine and cosine's derivatives. It's possible to do it that way, and I sketch that out in the book, and I definitely encourage you to follow that argument, both because it is a beautiful argument in and of itself, and also because it will teach you a lot about the tangent function itself, quite independent of its derivative. But what I want to do here is not so much a beautiful proof as just an algorithmic one, because that will give us the opportunity to practice the quotient rule. And you might say, well, where's the quotient? This is just one function. Ah, but you know from trigonometry that tangent is equal to sine over cosine. So I can think of tangent as a quotient. And to take a derivative of a quotient, we just follow the quotient rule, which we remember by this silly poem. So let's see, low d high minus high d low. That's going to be cosine times the derivative of sine minus sine times the derivative of cosine, since cosine x is low and sine x is high. Anyway, low d high minus high d low over the square of cosine x. So this equal sign is justified by the quotient rule. Now we just need to take those derivatives and clean this up. Well, the derivative of sine x is cosine x, and the derivative of cosine x is minus sine x. We can clean up this numerator by writing this bit as cosine squared x, and this stuff in here as plus sine squared x. And the denominator just comes along for the ride. Well, if there is one trigonometric identity that everyone knows, it's the Pythagorean identity. Cosine squared x plus sine squared x is, of course, 1. And now we have this in a tidy form, but it can be even tidier. 1 over cosine x is secant x. So 1 over cosine squared x is secant squared x. And this is the result we were after. I'll record it over here. The derivative of tangent x is secant squared x. This isn't quite as easy to remember as these two, but it's pretty easy, and you need to get it in your head. So say it to yourself 20 or 30 times until you've got it. All right, well, this was a nice example of how the quotient rule works. Especially nice since instead of just applying it to a quotient of two functions we don't particularly care about, we obtained a new important result in using it. And in fact, we could use the quotient rule to come up with the derivatives of the three reciprocal trig functions, secant, cosecant, and cotangent. Let's do one of those now. Let's get cotangent of x's derivative. Well, to get this with the quotient rule, we would need to write this as a quotient, which is easy since this is the reciprocal of the tangent function. So we can rewrite it as 1 over tangent. And now I've got a quotient of functions, one function of which is very boring, the constant function 1. So to take its derivative, I can apply the quotient rule. Well, let's see. Upstairs we get low d high minus high d low. That's this stuff over the square of what's below, tangent squared x. So this is what we got from the quotient rule. Now we just need to simplify this mess, which is easy. Look at the first term. It includes, as one of its factors, the derivative of the constant function 1. Well, the derivative of any constant function is 0, because derivatives measure rate of change, and constant functions don't change. So that whole piece right there is 0. As for what remains, we've got a minus 1, well, the 1 isn't doing anything, times the derivative of tangent. And we just proved that the derivative of tangent is secant squared. So this second term just becomes minus secant squared, and that's our numerator now. Downstairs we still have tangent squared x. Well, in one sense, we have found the derivative of cotangent, but it's ugly. We can clean this up quite a bit. The easiest way to do that would be to turn everything into sines and cosines. Secant is the reciprocal of the cosine function, so I could rewrite the numerator as minus 1 over cosine squared x. Tangent, we've said, is sine over cosine, so I could rewrite the denominator as sine squared over cosine squared. And we can simplify this by doing the division, invert and multiply, and we end up with minus 1 over sine squared x. And this can be crunched down further, because the reciprocal of the sine function is, of course, cosecant, so we have cosecant squared and negated. That is, this all turns out to be negative cosecant squared x, which is as good as this gets, so I will put it over here in our collection. And there it is. And what we just did here to come up with the derivative of cotangent, we could also do to come up with the derivatives of secant and cosecant, because secant can just be written as 1 over cosine, and cosecant can be written as 1 over sine. To take those derivatives, we just apply the quotient rule and use some trigonometric identities to arrive at fairly compact expressions on the other side. I'm going to leave those two as exercises for you, though I'll state the results in a few minutes. And while it might look like we are piling up a lot in this lecture for you to memorize, it's not that much really. The product rule is easy. You probably already have that one down. The quotient rule looks like a mess symbolically, but if you remember the little jingle, low d high minus high d low, then that's easy too. As for the derivatives of these 6 trig functions, well, 2 of them you know already, the derivatives of sine and cosine. Tangent is not hard. The derivative of tangent is secant squared. Say it to yourself 100 times, whatever it takes. But yes, that's one you'll have to memorize. But the derivatives of the 3 reciprocal trig functions are actually pretty easy to put in your head. The trick is to remember that the 6 trig functions not only come in reciprocal pairs, like cotangent and tangent, cosine and secant, and sine and cosecant, but they also come in cofunction pairs, sine and cosine, tangent and cotangent, secant and cosecant. And there's a very simple pattern among the derivatives of cofunctions. Let's look at our first pair, sine and cosine. Well, the derivative of sine is cosine. The derivative of cosine picks up a negative and switches from cosine to sine. So those 2 things are happening over here in derivative land. The derivative of this cofunction gets a negative, and what was cosine becomes its cofunction, sine. And so much for the first pair of cofunctions. Let's look at the second pair. The same pattern holds here as held here. The derivative of the relevant cofunction, cotangent, picks up a negative, and where we had secant before, we get its cofunction, cosecant. And guess what? The exact same pattern will hold for our third pair of cofunctions. I'm not going to write out the details. In fact, it's an exercise in the book, but you can determine very easily what the derivative of secant is. And you should be able to prove that secant's derivative is secant x times tangent x. This is another one you just have to get in your head. But once you have it there, and we've seen this pattern among the derivatives of cofunctions, I'll bet you can guess what the derivative of cosecant is. Well, it's going to have a negative, and for each trig function we had here, we're going to get its corresponding cofunction. So instead of having secant x times tangent x, we're going to have cosecant x times cotangent x, and again with that negative out front. So noticing that pattern makes it considerably easier to remember the derivatives of the 6 trig functions. Good. There's one more thing I want to do with the quotient rule. We've already used it to get the rest of the derivatives of the trig functions, but I can also use it to extend the power rule that we learned a while ago. So let's extend the power rule to negative integer exponents. We already know that when we have a power function with a positive integer exponent, we can take its derivative simply by bringing the exponent down in front and then reducing the exponent by 1 to give us this expression. Now my claim is that the power rule extends to negative integer exponents, so that if we take the derivative of x to the minus n, where n is any whole number, then the same result holds. I claim we can get the derivative by pulling the exponent down in front and then reducing this exponent by 1. So that this derivative should turn out to be minus n times x to the minus n minus 1. Well, that would be nice if it were true, and I can claim any damn thing I want. The question is, can I prove that it is so? I can, because the derivative of x to the minus n is something we can obtain from the quotient rule. We just have to recall the definition of x to the minus n. That symbol means 1 over x to the n. And so now I've actually expressed it as a quotient of 2 functions. As with the last one we did, the top function is a very boring one right here. It's the constant function 1, but we can still use the quotient rule. When I apply it, I get low d high minus high d low over the square of what's below. I actually like to fill in the bottom first because that's the easiest part. When we square x to the n, of course, we get x to the 2n. As for the top, we get this stuff. That is our low d high minus high d low that the quotient rule gives us, and it simplifies considerably. Once again, this first term disappears because we have the derivative of a constant function, which is 0. That whole term is gone. While over here, we get negative of the derivative of x to the n, where n is a whole number. So I already know how to take that derivative by the earlier case of the power rule. This is the familiar case of the power rule that we've already proved. So what I'm going to end up with in the numerator is this, while this just comes down. So this holds by the version of the power rule that we've already established, the case where the exponent is a positive whole number. And this expression can be simplified by combining these x's using the usual law of exponents. Doing so gives us minus n, that's just that factor there, times x to the n minus 1 minus 2n. And now we can do the arithmetic right there and all of this becomes minus n times x to the minus n minus 1, because that n minus 2n gives me minus n. And that is precisely what I was claiming it should be, as claimed, and we are done. So now we know that our power rule holds for all integer exponents, positive or negative. For example, now we can say that the derivative of x to the minus 3 can be obtained by bringing this out front and dropping the exponent by 1, so that we end up with minus 3 times x to the minus 4, which of course we could also write as minus 3 over x to the 4th, should we desire to do so. Or how about this? Suppose we're looking for the derivative of 5 over x to the 6th. Now, the really tedious way to take this derivative would be to apply the quotient rule. It will get you to the right answer, but it's a pain. Before you take any derivative, you should always ask yourself if there's a way to simplify the expression first by using algebraic or trigonometric identities. Make sure you're thinking about problems before you just start grinding out answers. Anyway, in this case, rather than using the quotient rule, we could just rewrite this expression as the derivative of 5 times x to the minus 6th. And once we have it like that, we clearly don't need the quotient rule. We can just use the power rule, which gives us in one shot that this derivative is minus 30, minus 6 combining with the 5, times x to the minus 7th, because we've reduced the exponent by 1. And if you want, you could always rewrite that as minus 30 over x to the positive 7. It might be a good exercise actually to stop and do this with the quotient rule, see that it's a bit more of a pain, and confirm that you do end up with the same answer though. But as I say, always be on the lookout for ways of simplifying a function before you take its derivative. And with that in mind, let's do one last example, which is a special one that comes up a lot. Let's find the derivative of the reciprocal function. Well, again, we could do that directly with the quotient rule, but that's a bit of a pain. Much easier just to rewrite this expression as x to the minus 1. And now to take its derivative, I can just call on the power rule, which tells me that the derivative will be minus 1 times x to the minus 2, because I've dropped the exponent by 1 when I take that derivative. And this is ugly, so let's rewrite it as negative 1 over x squared. Now, this derivative comes up so frequently that it is well worth your time memorizing the result. True, it only takes a few seconds to go through this argument each time, but it's much nicer just to have the result right there in your head. So if we forget about the intermediate steps and just summarize the final result, we end up with this. The derivative of the reciprocal function is minus 1 over x squared. A good one to get in your head just for the sake of efficiency. Oh, and one last thing. In the exercises in the textbook, you'll see that we can extend the power rule even further. There, I sketch out a neat trick that allows you to extend the power rule to the case of all rational numbers, thus proving, for example, that if we wanted the derivative of x to the 22 over 7, all we would have to do is bring that 22 over 7 down in front and then reduce the exponent by 1, which would give us 15 over 7. Please do that exercise, and I hope you will be able to savor the proof, which is quite neat. And that too has one special case like this that's worth mentioning, because I'll probably use it in future videos. Just as the reciprocal function comes up all the time, so does, of course, the square root function. And if we want to take its derivative, we can do so by using the extended power rule that you will prove in the exercises. Because, of course, the square root of x is the same thing as x to the 1/2 power. And by that extended power rule, that means that the derivative will be half x to the power of, well, we have to reduce 1/2 by 1, which brings it to minus 1/2. And we can then rewrite this expression. X to a negative power is 1 over x to that positive power. So this is 1 over x to the 1/2 power, or in other words, 1 over the square root of x, which means this whole thing becomes 1 over 2 times the square root of x. Just like this business with the reciprocal, this is a result well worth memorizing. The last one, I promise, I will give you in this lecture. So I will summarize it in its own little blue box. And there it is. And that is all. Please remember, when you're studying this stuff, to create a coherent story in your mind that puts it all together. Don't just try to memorize all of these without any context. Try to remember where it all comes from. These, for example, are just special cases of the power rule. And you memorize them just to make your own work quicker and your life a little easier. These derivatives of the trig functions are not as hard to remember as they look because they fall into nice patterns that we talked about earlier. You already know two of them. We've already said many times today that the derivative of tangent is secant squared. Hopefully that will be easy to memorize. If you understand the cofunction pattern, that gives you the derivative of cotangent immediately. You don't really have to memorize it separately. You do have to memorize the derivative of secant, and you still need to derive that because we didn't do that here. But once again, if you know that cofunction pattern, you get the derivative of cosecant for free. It's not really something extra to memorize. The quotient rule you know by the dippy verse here. The product rule is easy. And as you probably gathered from this lecture and the last one, if your trigonometry is rusty, you do need to get that up to speed and quickly. It's a lot, I know. No one ever said learning calculus was easy. It isn't, but it is within your grasp. But only you can do the hard work of sitting down for hours at a time and thinking your way through this. But if you do it, you should be fine. And you should enjoy the process. There's so many nice ideas being tied together in this class. And you should have a sense of lots of disconnected bits that you learned in pre-calculus classes starting to come together and move a little bit. Take on life that you didn't know it had. And this sense will continue to grow the further you go into your mathematics courses, the deeper you go into the calculus sequence, and of course if you learn linear algebra and differential equations and beyond that. You are still at the very beginning of what should be a long, challenging, and enjoyable intellectual adventure. All right, the end. See you next time.